Today we're going to talk about the concept of force and Newton's first law, and these are things that you've already done in the IGCSE. However, it's very important that you understand those very well, that not only you know them, but you're familiar with them so that you can do the problems, which can get really abstract, as you will see. Now, what I told you in the IGCSE is that a force is just a push or a pull. So if I have a block of whatever here, now I can either push it forward, or I can pull it backwards, or up, or whatever. That's a force. So anything that pushes or pulls, be it at a distance, so like gravity does, or just by touching things, then that's a force. Now, of course, the definition of force is a little bit more abstract, and the basic idea is that a force is anything that can cause an acceleration. So if I cause this thing to accelerate, then I am exerting a force. Now, of course, sometimes I will exert a force and cause no acceleration, but that's because there's another force acting against me, and then the net force is zero. But the idea is that a force is something that can cause an acceleration of a body. And now you may be thinking, well, but some forces actually cause deformation, right? So I have a blob, and then I do a force this way, and then the blob gets deformed like that. Well, yes, but again, a deformation is just a particular case of an acceleration. So a force is anything that can cause an acceleration. Now, of course, one of the forces that you may be familiar with is weight. And we did this in the IGCSE. Now, before we go on, I would like you to pause this video and say out loud the units of weight. So please do that. Okay. Hopefully you did this, and I really hope that you did not say kilograms, because weight is not measured in kilograms. Kilograms are for mass. And what's the difference, you may say? Well, the difference is that weight is a force, whereas mass is the amount of matter that's in my body. So the amount of matter that's in my body that never changes. It's the same here and in the moon. The weight, however, is the force with which the planet is pulling me down. So different things. Now the units of weight are units of force, and hopefully you remember the units of force. So pause the video and say them out loud. Okay, hopefully you did as I told you, and you said that the units are newtons. Now remember, these are not pure units in the sense that they're made up of other smaller units. Now, you may remember from the IGCSE that force equals mass times acceleration, so newtons are actually made of units of mass times units of acceleration. Therefore, Newton is nothing but a kilogram times the units of acceleration, which are, pause the video and say it out loud again. Okay, hopefully you said meters seconds to the minus 2. So a Newton is nothing but a kilogram times meters times seconds to the minus 2. It's a compound unit for force. Now, the way to calculate weight is to multiply our mass times the field strength of gravity in here. What's the field strength? Well, the field strength tells us how many newtons per kilogram of force I receive if I'm on the surface of the Earth. So let me just show you this. Now, so here's the Earth, and the Earth is really massive, so whatever I put in here will receive a force, and this force will depend on how heavy this thing is. And I can give this a number in newtons per kilogram, like how many newtons will I receive per kilogram, and that's called the field strength. Funnily enough, a newton per kilogram is an acceleration. That's why we normally speak about the acceleration of gravity. But actually, we're not really talking about an acceleration. We're talking about a field strength. So the field strength on the surface of the Earth, we call it G, and it's 9.8 newtons per kilogram, which has units of acceleration, and therefore we call it the acceleration of gravity, which is 9.8 meters second to the minus 2. But remember, what we're really talking about here is field strength. How much force per kilogram does something receive when it's on the surface of the Earth? Okay, so imagine that I weigh 100 kilograms. So, well, I weigh 100 kilograms, that's speaking of course informally. My mass is 100 kilograms. So what's my weight? Well, if the field strength is 9.8 newtons per kilogram, means that for each kilogram I'm going to get 9.8 newtons of force. So I just need to multiply these two things to get my weight. In this case, my weight is going to be 9.8 times 100, and that's going to be 980 newtons. Now, a lot of the time we will just take the field strength to be 10 because we can't be bothered. But be aware that it's actually 9.81 newtons per kilogram. Another force that, believe me, you're going to be seeing a lot of is tension. And tension just is the force that is made on a string and by a string. So imagine that I have a string like here, like this, and I'm pulling both ends with the same force. Now what this creates is a force between, at any point of the string, going this and this way. And this is due to the fact that the string reacts to the force that I'm doing pulling it here and then has to pull back. If it didn't, then it would just break. I can understand this if I imagine that the string is made of many little chains put together, and then what's happening is that I am pulling this one, which in turn is pulling this one, but this one is also being pulled by this one, which was being pulled by this one, and so on and so on and so on. So at each link in the string, there's a force this way and there's a force this way, and they have to balance each other out, otherwise the string would break. Now, another type of force that you're going to be seeing a lot of is a normal reaction force. And a lot of people think that normal reaction forces are the opposite of the weight, but that's not true. The idea is that the normal force is the force that a certain body, like a ground, will do in order to prevent some other body to go through it, from going through it. So for example, imagine that I have this block here that is creating a certain, well, has a certain weight. So this thing is trying to go down. But of course it can't go down because there's the ground here. So how can this thing prevent this body from going down? Well, the only way is by doing a force that's exactly equal to this force that goes down, but on the opposite direction. When this happens, these two forces will balance out, and then this thing is not going to move. Now, of course, this happens in this case because this is horizontal here in the surface. But what if the surface is like this? Well, in this case, the weight goes still down, but there's a component of the weight, this one, that's actually not trying to get through the ground. So the ground doesn't care about this component at all. This is just going to make this move this way. All that the ground cares about is this component on the weight, the one that's pointing perpendicular to it. Now, remember that normal means perpendicular, so that's why we call this a normal force. We have that the normal component of the weight has to be balanced by this normal force, which will be equal not to the weight, but just to this component over here. Now, how would I go about calculating this? Well, using some good old trigonometry, and I'm sure you're going to love this. If this is an angle theta, I know it looks like a 0, but it wants to be a theta. Okay, so if this is an angle theta, this is 90 degrees, and therefore this is 90 minus theta, which means that this angle here is theta also. So let me just show you that this is theta. And I want to calculate this component of the force here. Now, in order to do this, I get the normal, which is the hypotenuse, and I need to multiply it by some quantity. Will it be the sine or the cosine if I want the horizontal projection? Pause your video and say it out loud. Well, hopefully you said the cosine, because this is obviously the cosine of this angle. Therefore, if I want to get this normal force here, I need to multiply the weight times the cosine of the angle, which is the same angle as this thing. Don't worry about this if you don't get it right now. It will be coming up later on, but it will be coming up a lot when we do Newton's second law. Now, another classic force are drag forces, and these ones oppose the motion of a certain body through a fluid. So for example, my car is trying to go through air with a certain velocity v, and it's going, because of this, the air is hitting the car and slowing it down, creating a drag force called air resistance. Now, this also happens, for example, if you go through water or basically any fluid. When I try to move through a fluid, the molecules will hit me and create a resistance to the movement. Now, what happens with this is that this depends on the velocity of the body, because of course the faster that I move, the more that I get hit by molecules and the more resistance that I have. And this makes drag forces very hard to analyze mathematically. So we will be doing very little of this using math, but we will be doing some of this in a qualitative way. So like more or less what's going to happen. We're not actually going to calculate anything with drag forces because it's way too complicated, our mathematical level. Apart from drag forces, we have something called upthrust in fluids. So upthrust, I think we also saw that in the IGCSE, so you should be familiar with this. Upthrust is just the force that a certain fluid will do to a body in order to make it float. So for example, if I have a little ball on the water, it doesn't go down, and the reason it doesn't go down, even though it has a weight, is that the water is pushing it up with a certain force. That force is called upthrust. Now you're going to be seeing a lot of friction forces, and remember that friction forces are just the forces between two surfaces when one is trying to move on the other. Now what happens is that if I start pushing this block here, at the beginning this block is not going to move. And the reason why this is happening is that this, if I zoom in, is rough. And because it's rough, like this, these parts, push on each other, and the whole thing does not move. Now, however, there will be a point when the force that I do is enough to get this to start moving. This is the maximum friction force. So this will do a friction force that's exactly equal to my force until I reach this maximum friction force. Now, while this is not moving, we call this static friction forces because there's no movement. However, once this thing starts moving, then the friction force gets highly reduced, and the reason is that there's air between here and here now, and therefore the forces between these little bumps are a lot less. So the friction comes then kinematic or dynamic, or kinetic, sorry. So kinetic or dynamic friction forces, whatever you want to call them. And they are usually, well, always smaller than the static friction force. So for example, this could have a maximum static friction force of, let's say, 50 newtons. Then once I reach these 50 newtons, there will still be friction, but it will be normally around 20 newtons, way less than how hard it was to get this thing to start moving. Another really important force that you're going to see a lot of is the force that springs do when they get either compressed or stretched. And that force is described by something called Hooke's law. And this is very important because this kind of force creates an oscillation motion. And oscillation are the basis for waves, for example, and also for circular motion. So basically from this law you can derive the basic equations that relate to a lot of physical phenomena that go way into what people are studying today. So what happens here is that the more that I stretch this thing, so let's just say that I'm stretching this by a certain amount x. Now the more that I stretch this thing, the more that the spring wants to go back to its original position. So what we find is that the force is proportional to the stretching. And we can write this as force equals k times x, where k is a constant that will depend on the string. So a very strong string will have very high k. A very weak string will have very low k. Now that we know a bunch of forces, we can finally go into Newton's first law that basically tells us a condition for equilibrium, which is how do we know that a body is either still or moving at a constant speed? And again, you did this in the IGCSE, and hopefully you could stop the video and tell me what Newton's first law is. If you don't remember, don't worry, thankfully we're doing this again. So imagine that I have a bunch of forces acting on this thing at different angles, and I want to know whether this thing is going to move or stay still or move with a constant speed. What Newton's first law says to me is that if I add up all these forces and the resulting force, the total force is 0, then this body will either be still or move with constant speed. Otherwise, this body will be accelerated. So remember, lack of force does not mean being still. A lack of force means no acceleration. So let's make this into a motto. No force means no A. But it can mean that there's a velocity. It's no problem having no force and a velocity. All that means is that when there's no force, there's no acceleration. And conversely, if there's no acceleration, it means that there's no force. And by no force, I mean that the total force, of course, is 0. Now, in order to find out whether there's no force, we need some kind of tool. And that's given to us by free body diagrams. And a free body diagram is just drawing all the forces on the body. But there's a certain way to do this. You can't just do it any way you please. Now, the idea is that every time that we consider one of these bodies, we make a simplification. We assume that they're really a point object, so that all their mass is located in the center of mass. So all the forces really apply to the center of mass. Now, this thing that I'm telling you, later on I'm going to say that it doesn't go, and it's not because it's wrong, it's just because this is an IB peculiarity where sometimes they like to see the friction forces along the surface. Don't ask me why, it makes no sense, and as a physicist it makes me cringe, but it's just the way it works. So anyway, so imagine that here's my ball, and it's on the ground. So what forces are acting on it? Well, first thing, I would have gravity is pushing it down, and then I would have the normal force is pushing it up, and that would be it, right? Or this is a free body diagram. Or I could have same thing, but I could have it on a surface. So here's my surface, here's my block, and again I would have gravity, and then here I would have the normal force. Remember, that's normal to the surface, and maybe there would also be the friction force this way, if there was friction. I could also, for example, draw a little string, and then to the friction force I would have to add the tension of the string, and so on. So this is how you draw a free body diagram. You just find all the forces that are acting on the body, find their direction, and draw them coming out of the center of mass of that body. Alright, so we're done for today. This is what you should be able to do by the time you come to class. You should know the difference between mass and weight, and also the different units. You should know what gravitational field strength is and give its unit. Remember that that's what we usually used to call the acceleration of gravity. Draw vectors representing forces acting on a body. So remember, you draw the body, draw the little vectors coming out of its center of mass. Identify and draw frictional forces, so you need to know when there's friction and then draw the frictional force. Use Hooke's law. Remember, you have a spring, the force is proportional to how much the spring is stretched or compressed. And finally, state and apply Newton's first law, which we just did. So hopefully you know how to do all this, and you can get started with the problems, which, believe you me, are not easy. Good luck.